Hello everyone, welcome to Jigyasa's video tutorial series. The last video we had seen the implementation of modulation schemes in 5G-NR using Toolkit 5G. Similarly, in this video, we'll be seeing the implementation of two channel coding algorithms in the Toolkit 5G. To have a very simplified bird's eye view on what channel coding is, it is a crucial technique in communication systems designed to improve the reliability of transmission. So what's the key objective of this technique? It's error detection and correction. So how exactly is that accomplished? It is done by strategically introducing redundancy bits in the message bit. So what are the two different kind of channel coding algorithms that are going to be seen in this video? We'll be looking into the polar codes and LDPC codes, implement the same using Toolkit 5G and analyze their behavior. So let us start with polar codes. Polar codes are used for forward error correction, and essentially with respect to 5G they are used in two channels, the broadcast channel and the control channel. What are these channels characterized by? Essentially, they have very small to medium payload sizes. To be specific, the broadcast channel and control channel are used to carry the master information block MIB and the downlink control information DCI, which are the medium payload sizes which undergo polar coding. So how exactly are we going to perform polar coding using the Toolkit 5G? Initially, as we had seen in the last video, we will be importing all the subsidiary libraries of Python that are required. Then from the 5G Toolkit library, we will be using 4 modules. The mapper, demapper, which we had dealt with earlier, and specifically for this experiment we will be getting an intro on polar encoder 5G and polar decoder 5G. Here we are going to perform QPSK modulation, and on the receiver side we are going to perform a log map decoding. So that's all the information concerned with the symbol mapping. Let us move on to the polar coding part. So what are the different simulation parameters that the polar coder requires? First we need to define the block length, then we have to define the rate matching bits, or to be more specific, what is the target bits, total number of bits at output. And then as I mentioned earlier, both control channel uplink and downlink and the broadcast channel utilizes the polar code. Therefore, which purpose is the channel coding being performed for here, and what purpose does essentially is state whether you need the working or print statements to log the functioning. Finally, we have a successive cancellation decoder. To get a more detailed definitions of what these parameters are and what significance they hold, you can visit the API documentation for Toolkit 5G present in the Jigyasa website. And in polar codes, basically we give an example of what polar coder is, how to perform it, and then you could have what are the parameters that are to be passed and what are the inputs, and then what is the output. The parameters, as I had mentioned earlier, are K, E, purpose and verbose, and the input is the channel bits that are to undergo the polar encoding, and the output will be the channel coded bits. Also under decoder, these are the values that are to be given, that is the number of information bits, the number of target bits, the polar decoder type, and then what was the CRC type used, and then the purpose, followed by the input, which is the 2D array containing the LLR values. Finally, in the output we have a value containing the hard decided estimates of all K information bits. So this is the simulation that we are performing. So what exactly are we doing here is twofold. First, we are increasing the K and maintaining E at the same value. Essentially, there is a parameter called as code rate, which is the ratio of K by E, and we are increasing the code rate and seeing how the channel coding algorithm performs. By doing so, this is the log of the entire performance, and this is the plot that we get. If you can see here, as the block length increases, or in other words, as the code rate increases, the BR performance deteriorates. Why is this so? Basically, when the code rate increases, it means the number of redundancy bits reduces, and when the redundancy reduces, the reliability of the channel encoding process reduces, thereby showing this performance. And there is another thing that we have to do. That is, here if you can notice, we are increasing both K and E proportionately. And that means the code rate will remain fixed throughout the different iterations. And then we are going to check for different block lengths what is the BER performance. Again, if you can see here, you will notice that as the block length increases, the performance deteriorates. So despite the code rate being normal, this is the behavior that can be noticed. I would like you to keep this in your mind, and when we are going to implement LDPC for the same condition, we can have a comparative study of both and then cycle back to one of the earlier informations that we told, thereby having a complete cycle of information. So let us go to the LDPC codes. So LDPC codes are again used for forward error correction, but in this case this is used for shared channel. So why is that so? These are asymptotic. These channel codes are asymptotic, meaning they achieve channel capacity for large block lengths essentially when the block length reach towards infinity. So moving on, this is the as usual we have imported Python. So this is the as usual we have imported Python libraries, and if you can see over here, there's another interesting thing that is being done here. What we are doing is importing a thing called as LDPC parameter. Why is that so? If you can take a look over here in the LDPC page, the input parameters for LDPC are k. Other than k, the number of information bits are bg, which is the base graph, and the lifting factor. So this is based on the different guidelines and formulas set by the 3GPP. And in order to get a 3GPP compliant k, bg, and zc combination, you can use the LDPC parameter computation. Essentially, this gets the transport block size, code rate, and let to determine the base graph, the number of input bits to LDPC encoder, size of the LDPC code word, and finally size of the code word generated by the LDPC coder before the truncation and after the truncation, and also the factor ZC, which is the lifting factor. So that's what we are doing here. We are calling the LDPC parameters to get the configuration, and using the configuration we are again performing the two types of analysis. The first one is for increasing code rate, that is the block length is increased while keeping the target bits at the same. And if you see for increasing code rates, again as explained earlier, the redundancy reduces, thereby leading to a deterioration in the performance. And however, for the second case where we have a fixed code rate, what can be witnessed is for the larger block lengths, better performance is achieved. So what is happening here? This is an illustration of the previously mentioned fact that LDPC is asymptotic, or it achieves channel capacity for larger block length. Hence, for the shared channels which have larger block lengths, we are using LDPC, whereas for the control and broadcast channels which have medium to small payloads, we use the polar codes. I hope you have had a clear understanding of what channel coding algorithms and their implementation using Toolkit 5G. For any doubts regarding the implementation, you can contact the Jigyasa team. Thank you.